somewhere far above the noise of the day, past the last thin breath of atmosphere, past the moon, past the sun, past the outer worlds of ice and stone, the sky opens into something quieter than quiet. The stars thin out, whole galaxies become soft grains of light. And if you could keep going, farther than any ship could ever carry you, you would come at last to the edge of what we can see. Not the edge of the universe itself, only the edge of the part whose light has had time to reach us. That boundary is called the observable universe. It is a soft sphere of visible sky, drawn not by walls, but by time. Beyond it, more universe surely continues, yet even the light from those farther places has not arrived here yet, and may never arrive. So we sit inside a bubble of vision, listening to the faint hum of everything we can measure, and we ask a simple question: where did all of this come from? Modern cosmology gives us a strange and beautiful answer, and then it stops. The answer is that everything we see, every galaxy, every long river of stars, every dark stretch between them, once fit inside a region far smaller than an atom. Then, in a moment so brief that words strain around it, that region grew. It grew faster than anything grows now. This burst of growth is called cosmic inflation, and the evidence for it is written softly into the oldest light in the sky. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like, one waiting each evening, subscribe and let it find you. But inflation is not the beginning. It is only the first chapter we can read. Before inflation, something else must have existed, or something else must have not existed, or perhaps neither word quite fits. That is the mystery we will sit with tonight. Not what came after the first moment, what came before it. What was the state of the world when there was no world yet? What kind of thing gave rise to a beginning at all? There are several careful ideas. Some researchers wonder if the pre-inflationary universe was a quiet, high-energy field, waiting like a still pond for a ripple. Others picture a bounce, an older universe that collapsed down and sprang back outward, our inflation being only the freshest breath of a longer rhythm. Still others suggest that time itself did not exist before inflation, so the word before may not even apply. Each of these ideas is serious. None of them is settled. The evidence so far is thin, and the mathematics is honest about how little it knows. Picture for a moment the sky as it looks from a dark valley on a clear night. The stars seem fixed. The galaxies drift so slowly that a whole human life sees no motion in them at all. Yet all of it, every point of light, is the long echo of that first swelling. Every galaxy was seeded by tiny ripples that grew during inflation. Every empty patch of sky was smoothed by it. The bones of the cosmos, its shape, its flatness, its evenness in every direction, all seem to trace back to that single stretching moment, and behind that moment is a curtain we cannot lift. Not yet, perhaps not ever. Physics, at its most honest, admits that the laws we trust today may break down at the door of inflation. Our best theories describe what happens after the first tiny fraction of a second. Earlier than that, the equations blur: time, space, energy, cause and effect. All of these words begin to lose their normal meaning. We are left standing at the threshold of the universe, holding a lantern that only shines so far. Tonight, we will walk slowly toward that threshold. We will look at what inflation is and what it explains. We will look at the ideas people have offered for what may have come before it. We will meet false vacuums and quantum foam, bouncing universes and colliding higher dimensions, and proposals in which the beginning has no edge at all. We will not solve the mystery. No one has, That is part of the pleasure of thinking about it. For now, settle in. Let your shoulders soften. Let the room grow a little dimmer in your mind, somewhere above the ceiling, past the roof, past the clouds, past the moon. The universe is going about its slow, ancient business. And underneath all of it, quietly waits an unanswered question, a question old enough to hold you gently while you drift. Before we sit with the mystery of what came before, we should spend a quiet moment with the thing itself. Cosmic inflation. The word sounds gentle, and in some ways it is, but the picture behind it is one of the strangest ideas in all of science. Let us walk through it slowly, the way you might walk through a dim garden at dusk, noticing one shape at a time. Inflation is the name we give to a very short burst of stretching that seems to have happened at the very start of our universe. Not stretching in the way a rubber band stretches, stretching in the way space itself grows larger, carrying everything inside it along for the ride. The best guesses place this burst in the first tiny sliver of the first second of time. And when we say tiny, we mean something almost impossible to picture. The stretching may have begun around a trillionth of a trillionth of a trillionth of a second after the clock of the universe started ticking. That is a decimal point, followed by more than 30 zeros before the first real digit appears. In that brief flicker, space is thought to have doubled in size, then doubled again, over and over, perhaps 60 or more times. If you doubled a single grain of sand 60 times, you would end up with something far larger than the visible universe. That is roughly the scale of stretching we are talking about. A region smaller than a proton, smaller than an atom's heart, blown up in an instant to something bigger than a galaxy, and then, just as quickly, the stretching slowed down, and the universe settled into the calmer expansion we still see today. The reason scientists take this strange idea seriously is that our universe has three curious features that inflation seems to explain. The first is smoothness. When we look out into deep space, in every direction, we see roughly the same temperature and the same gentle sprinkle of galaxies. The far left of the sky matches the far right, even though those two regions have never had time to talk to each other, never had time to share heat or share light. Something must have made them alike before they were pushed apart. Inflation offers exactly that. A tiny patch, all at one temperature, stretched so fast that its evenness got spread across the whole sky. The second feature is flatness. Space, on the largest scales we can measure, looks flat. Not flat like a table, but flat in a deeper sense. Parallel lines stay parallel, and the angles of enormous cosmic triangles add up the way you were taught in school. There is no reason the universe had to be this flat. It could have been curved like the surface of a ball, or curved like a saddle. Inflation smooths out any early curves, the way stretching a wrinkled sheet across a huge bed pulls it tight. The third feature is the pattern of tiny lumps. If the early universe had been perfectly smooth, no galaxies would ever have formed. There had to be small ripples in the density of matter, seeds around which gravity could later gather stars and clusters. Inflation predicts these ripples too, born from tiny quantum jitters that got stretched up to cosmic size. The pattern of those ripples, printed onto the oldest light in the sky, matches what inflation would have made. Not perfectly, but well enough to keep the idea alive after decades of testing. To drive all this stretching, physicists imagine a kind of energy field filling that first fraction of a second. They call it the inflaton field. We have never detected it. We do not know what it is made of, or whether it is one field or many. It is a placeholder, a mathematical guest we invite to the party because the numbers seem to need one. Some researchers wonder if the inflaton is real at all, or if some other mechanism did the work. So here is where we stand tonight. Inflation is a beautifully successful story about a moment we cannot reach, powered by a field we cannot see, running for a length of time we cannot measure. Directly, ear tells us why the sky looks the way it looks. It does not tell us how it began. It does not tell us what set the field in motion, or what was there when the stretching started, or whether there was any there at all. That is the doorway we are standing at. Inflation is our best map of the first flicker. But maps have edges, and beyond the edge of this one lies the quiet question that will keep us company through the rest of the night. Every story of beginnings runs into the same soft wall. When we look back through the history of our universe, we can trace things quite far. We can follow the light of ancient galaxies, the slow cooling of hot gas, the faint hum left over from the young cosmos. But at some point, the trail thins. We reach a place where our instruments simply cannot see, and our equations start to tremble. That place is the wall of inflation. It sits at the very first sliver of time, a moment so brief that words strain to describe it. Somewhere within that tiny opening, space itself is thought to have stretched at an astonishing rate. Yet the wall is not just a matter of distance or brightness. It is a wall built out of physics itself, out of the way that heat, light, and matter behave when pressed to their most extreme conditions. Think of it this way. The universe we can observe today is like a wide, calm lake. If we drop a pebble at the far shore, ripples travel across the surface and eventually reach us. Those ripples are the ancient light and sound of the early cosmos. But if the surface of the lake was once boiling, churning, and hidden under a thick mist, no ripple from that time survives clearly. The mist is our wall. Inflation, if it happened, was that boiling moment, and whatever came before it lies on the other side of the fog. To understand how strange this wall is, picture the conditions that would have been needed. The early universe had to be small beyond imagination, denser than any lab could ever recreate, and hotter than the core of any star. In such a state, the familiar rules break down. Particles and forces we know today may not have existed yet. Space and time themselves may have been woven together in ways we cannot picture. It is a birthplace so strange that even calling it a place feels wrong. Some researchers think of this earliest moment as a kind of quiet spark. In their view, a small patch of space carried a peculiar form of energy, and that energy pushed outward with almost unimaginable force. The patch grew, doubled again, and kept doubling in the tiniest fraction of a second. In this picture, everything we see today, every galaxy and every star, came from that first small spark being stretched to enormous size. Others suggest a very different opening. They wonder if the universe did not begin with expansion at all, but with contraction. Perhaps space was falling inward before it began to fly outward. Perhaps a great squeeze reached its limit, bounced, and only then handed the story over to inflation. In that picture, the wall we cannot see beyond is not a birth, but a turning point, and something older lies behind it. Still others hold that no beginning story quite fits, and that our idea of a first moment is misleading. Time itself, they argue, may not have started as a clean line with a starting dot. It may have curved gently into being, the way the surface of a sphere has no true edge. In such a view, asking what came before inflation is a little like asking what lies north of the North Pole. The question has grammar, but perhaps no answer. What all these ideas share is respect for the wall. None of them claim to see through it cleanly. Each is a careful guess about the conditions that had to be just right for our universe to unfold as it did, and each accepts that those conditions, whatever they were, remain hidden behind that early fog. There is something quietly humbling about this. We can measure the temperature of light from nearly 14 billion years ago. We can map the faint patterns of hot and cold across the sky. We can even guess the shape of ripples that inflation may have left behind. Yet, the moment just before those ripples formed keeps its secret. Our best telescopes, our finest satellites, our most careful mathematics all slow down when they approach it. Perhaps the wall will thin with time. New instruments may find faint signals threaded through the ancient light. New theories may reach into that first fraction of a second with sharper tools. Or perhaps the wall is truly final, a soft edge to what physics can ever say. For now, it stands where it stands, and we sit before it, gently curious, imagining the conditions that had to align, the forces that had to balance. The strange quiet or strange storm that must have come first, the story of how it was born, is still being written, one careful question at a time. To imagine what came before inflation, we have to reach for a strange idea from the world of quantum physics. The idea is called the false vacuum. It sounds like a contradiction, and in a way it is. A vacuum, in everyday language, means emptiness. But in physics, a vacuum is simply the lowest energy state a region of space can settle into. And here is the quiet twist. There may be more than one such state. There may be a lower one hiding beneath the one we know. Picture a small ball resting in a shallow dip on the side of a hill. The ball is stable. It is not rolling. To a casual glance, it looks as settled as anything could be. But farther down the slope, there is a deeper valley the ball has not yet found. Given enough time, or a small quantum nudge, the ball could slip out of its cozy dip and tumble toward that deeper place. The shallow dip is the false vacuum. The deeper valley is the true one. Some cosmologists wonder if the universe, before inflation, was resting in a false vacuum of its own, a patch of space filled with a strange kind of energy. Not empty in the plain sense, but empty of matter, empty of stars, empty of any of the things we now recognize as stuff. What filled it, instead, was a field, invisible and even, humming quietly at a high energy level. This field is often called the inflaton. It is still hypothetical. Its properties are guessed at more than measured. If that field existed, it would have behaved unlike anything in our daily world. It would have carried a pressure that pushed outward rather than pulled inward ordinary matter clumps under gravity. This field would have done the opposite. It would have stretched space itself, and stretched it fast, doubling and doubling again in tiny slivers of time. The false vacuum was the seed. The inflaton was the engine, and when the field finally slipped from its false resting place down into the true one, the stored energy poured out and became everything we can see. That, at least, is one story. It is a story built more from mathematics than from direct evidence. No one has ever detected the inflaton. No one knows its mass, its shape, or how many kinds of it there might be. Some models require one such field. Others require several, layered together like unseen instruments in a chord, and a smaller group of researchers wonder if the whole picture of a false vacuum is a useful fiction, standing in for something deeper we have not yet understood. There is a quiet beauty in the idea that the ingredients of our world came from a field rather than from matter. we tend to think of ingredients as tangible. The iron in the Earth's core was forged in the hearts of dying stars, then scattered by their final blooms of light. The water in the ocean may have ridden here on comets, cold and patient, arriving over millions of years. Every carbon atom in your body once floated in the wind of some ancient sun. Everything is on loan from something older. But the false vacuum idea reaches further back than any star. It suggests that before there were atoms, before there were quarks, before there was even the concept of a particle, there was only a field, resting in a metastable calm. All the mass and light we see today may be the released energy of that one long ago slip from a shallow dip to a deeper valley. If that is true, then iron and hydrogen and oxygen and every particle in the periodic table share a common ancestor that was not a thing at all. It was a state. Other thinkers push back on this picture. They ask how the false vacuum came to be in the first place. A metastable field must sit somewhere, in some kind of space, with some kind of physics already in place to define it. That does not sound like an absolute beginning. It sounds like a middle chapter, with the earlier pages still missing. And so the question quietly folds back on itself. If a false vacuum kindled our universe, what kindled the false vacuum? We do not know. The mathematics allows for the possibility. The evidence, so far, neither confirms nor rules it out. It remains one of several careful guesses, held gently by cosmologists as they peer at the faint edges of the observable sky. For tonight, it is enough to picture that shallow dip on an unseen hillside, a small ball resting in an ancient calm, and the long, quiet patience before the slip. Picture a stretch of empty space, not empty like a quiet room, but empty in the deepest sense you can imagine. No stars, no dust, no stray atoms drifting through. Just a pocket of nothing, sitting still in the dark. Now look closer, closer than any eye could ever see, closer than any microscope has ever reached. At that tiny scale, physicists believe the nothing is not really nothing at all. It is trembling, it is restless, it is alive with a soft, ceaseless motion that never quite settles down. This trembling has a name. Scientists call it quantum foam. The idea comes from the strange rules of quantum mechanics, the branch of physics that describes the smallest things in the universe. Down at that scale, the rules loosen, certainty fades. Even empty space cannot hold perfectly still. The reason has to do with a principle sometimes called the uncertainty rule. It says that certain pairs of properties, like energy and time, can never both be pinned down at once. If you try to measure a tiny region of space for a very short moment, its energy becomes fuzzy. It can borrow energy, briefly, from nowhere at all. And with borrowed energy, tiny particles can flicker into being, live for the briefest sliver of a moment, and vanish again before the universe has time to notice. Physicists call these flickers virtual particles. They pop in and out of existence in pairs, matter and antimatter, appearing together and cancelling each other out. This constant fizzing is not a wild guess. Its effects have been measured in delicate laboratory experiments, in the tiny shifts of light within atoms, and in the faint pull between two metal plates held almost close enough to touch. So even the deepest vacuum is not still. It hums, it shivers, it bubbles at a scale so small the numbers become dizzying. This restless nothing matters when we think about what came before inflation. Because if the very early universe was born from something like a quantum vacuum, and it was born from a place that could never truly rest, and in a place that cannot rest, unusual things can happen. Fluctuations can grow, regions of higher energy can appear, purely by chance, and if the conditions are right, one of those fluctuations might have been the seed of everything we see. One idea suggests that inflation began when a small patch of quantum foam happened to hold, for a fleeting instant, an unusually large amount of energy. That patch, filled with the energy of a scalar field we sometimes call the inflaton, could have started expanding on its own. Its own strange pressure would have pushed outward, doubling the size of that tiny region again and again, until a whole cosmos grew from a spark smaller than an atom. This is a beautiful picture. It is also only one picture among several. Other researchers wonder whether quantum foam is really the right way to describe the pre-inflationary state at all. The foam idea comes from combining two theories, gravity and quantum mechanics, that we do not yet know how to fully combine. At the scales where the foam is supposed to bubble, our current physics runs out. The equations stop giving clear answers. Some suspect that when we finally understand gravity at the quantum level, the foam might dissolve into something quite different, perhaps a smooth weave, perhaps a discrete lattice, perhaps something with no analog we can yet imagine. There is also the deeper puzzle of what the foam is actually made of. In our universe, quantum fluctuations happen inside space and time, but before inflation, space and time as we know them may not have existed in a familiar form. So what would it even mean for empty space to fluctuate if space itself had not yet settled into shape? The words begin to bend under the weight of the question. Still, the image of a restless nothing gives us something to hold on to. It tells us that in the modern picture of physics, stillness is not the natural state of the vacuum. Motion is. Even absence has a texture. The forces at work in that earliest moment were not the familiar tugs of gravity or the pull of magnets. They were subtler forces, quantum forces, the built-in shimmering of reality at its smallest scale. Whether that shimmer truly gave birth to inflation, or whether it is only a shadow of some deeper mechanism we have not yet uncovered, remains an open question. The foam may be the cradle of the cosmos, or it may be a placeholder, a stand-in for a truth still hidden from view. For now, we can only imagine that quiet, restless sea, humming softly at the edge of what physics can describe. The word before is a small word, only 6 letters. Yet when we press it against the beginning of the universe, it starts to bend and buckle in ways that are hard to hold in the mind. To feel why, we need to sit with the sheer scale of what inflation was, and how thin the sliver of time is where our question even makes sense. Picture a single grain of fine sand resting on your fingertip. Now imagine shrinking it, not by half, not by 1,000. Shrink it until it is smaller than an atom, then keep shrinking. Keep going until it is smaller than a proton, which is one of the tiny beads inside an atom. Keep going still until you reach a size so small that our best physics simply stops working. That size is called the Planck length. If you took the width of a single human hair and divided it into pieces, and then divided each of those pieces the same way over and over, you would need to repeat that division around 30 times to reach it. This is the scale where inflation is thought to have begun. Now consider the time. A second is short. A blink of your eye is quicker, but inflation lasted for something like 10 to the minus 32nd of a second. Written out, that is a decimal point followed by 31 zeros, and then a 1. If you sliced a single heartbeat into 1 trillion parts, and then sliced one of those parts into 1 trillion more, and then again into 1 trillion, you still would not have reached the length of the inflationary window. Whatever happened before that window is even harder to measure, because the clocks we know how to build stop making sense down there. Here is a way to feel the strangeness. Imagine that 1 second of ordinary time is stretched to equal the entire current age of the universe, roughly 14 billion years. On that stretched scale, the inflationary era would still be over almost immediately, and the moment we call before would be pressed so close to the starting edge that no ruler we own could pry it open. The expansion itself is just as hard to picture. During inflation, a patch of space smaller than a proton is thought to have grown, in that eye blink of an eye blink, to something at least the size of a grapefruit, and possibly much larger. That may not sound dramatic until you remember the starting size. It is like taking a single speck of dust and, in less time than light needs to cross an atom, swelling it to the size of a small city. And the expansion did not slow as it grew. It accelerated, doubled again, dozens upon dozens of doublings, each faster than the last. This is where the word before begins to lose its footing. Before usually means earlier. On a shared clock, you woke up before breakfast. The stars formed before the planets. But time itself, as we experience it, seems to be a feature of the universe we live inside, not a stage the universe was placed upon. Some researchers think time only becomes meaningful once space is smooth and large enough to carry a steady rhythm. If that is true, then asking what came before inflation may be a little like asking what lies north of the North Pole. The question has the shape of an answer, but the map runs out. Other researchers push back. They argue that some kind of time, or at least some kind of ordered change, must have existed to allow inflation to start in the first place. If a field had to settle into a particular state, or a bubble had to form in a wider sea, then something was ticking, even if it did not tick the way our clocks do. The tick may have been unimaginably slow, or unimaginably fast, or shaped in a way we have no words for. The question of whether that pre-time counts as time at all remains open. Hold the numbers gently as you drift. A patch smaller than an atom, a duration shorter than any instrument can measure, an expansion so violent it outran light itself, and yet so quiet that no sound could travel through it, because sound needed atoms that did not yet exist. Somewhere at the base of all that smallness sits our question, not what happened long ago, in years we can count, but what happened at a scale where years and seconds and even the idea of sequence may not yet have been born. The word before is the smallest word we have for this mystery. It may still be too large. Picture yourself somehow floating at the very edge of the universe's first moment, looking back toward whatever came before. You would not see darkness, because darkness is a thing that lives inside space, and space itself has not yet stretched out. You would not hear silence, because silence needs air to be absent from, and there is no air, no room, no here. What you might sense, if sensing were even possible, is a strange smoothness where the very idea of moment gives way. Time, in the way we know it, has not yet begun to tick. This is one of the strangest ideas in all of cosmology. Time may not be a fixed backdrop that has always existed. Time may be something that emerged, like frost forming on a cold window, only appearing once conditions were right. Many physicists suspect that before inflation began its brief and mighty stretch, the concept of before itself starts to lose meaning. The word points to nothing solid. Try to imagine the surface of that pre-inflationary state, if the word surface even applies. It would not be flat like a plane. It would not curve like a globe. Some theorists picture it as a shimmering fog of possibility, a soft haze where every event and non-event overlaps with every other. Others picture something more like a still pond with no ripples, no reflections, no top or bottom. The pictures we draw are only crutches. The real thing if it was a thing, resists any shape our minds can offer. One popular way to think about this comes from a proposal often linked to the physicist Stephen Hawking and his colleague James Hartle. In their picture, if you trace time backward toward the beginning, the timeline does not hit a wall. Instead, it curves gently, the way a line of longitude on a globe curves and meets itself at the pole. There is no edge, no first tick, no first anything. Time simply softens into another dimension of space. Standing at the pole of a globe, you cannot walk further north. There is no further north. In this view, asking what came before the universe is like asking what lies north of the North Pole. A competing picture treats time as more like a thread that was cut, not curved. In this view, time did have a starting point, a real first instant, and everything we can measure begins from that sharp edge. Whether that edge was inevitable or arbitrary is a question no one can yet answer. Some physicists find the sharp edge unsettling and prefer the smooth curve. Others find the smooth curve too clever, a trick that dodges the real question rather than solving it. Both sides agree we do not have the evidence to decide. If you tried to describe the color of this pre-time surface, you would fail. Color needs light, and light needs distance to travel across, and distance is another thing that had not yet formed. Some artists imagine it as a pearly gray, others as a deep violet, others as the color you see with your eyes closed on a quiet afternoon. None of these are right, and none of them are wrong. They are only the mind reaching for something to hold. The texture, if we can even speak of texture, might be closer to a temperature than a surface. Physicists sometimes talk about the earliest state as smooth in a very particular way, unusually so smooth that some, following the mathematician Roger Penrose, have argued that it looks suspicious. A truly random beginning should be lumpy and chaotic. Ours seems to have been polished, almost prepared. Why the universe began in such a low entropy, orderly condition is one of the deepest open questions in the field. It is possible inflation itself did the smoothing. It is also possible the smoothness was already there before inflation began, waiting like a fresh page. Standing above this scene, if standing were possible, you would notice one more strange thing. There would be no direction to fall in. Gravity, as we know it, does not yet exist. The forces that shape our world have not yet separated into their familiar four. Everything is still, folded together in a single, unified, whatever it was. To describe it in words is already to lie a little, because words are made for a world with time and space and cause and effect. So we sit on the edge, and we look, and we admit we cannot really see. Time is a latecomer to the universe, and the surface it arrived upon is a surface without a shape, a place without a place. What it truly was remains, for now, beyond the reach of any telescope or equation. For a long time, when people spoke of the beginning of the universe, they used a single word to describe it: singularity. It's a strange word, and a slippery one. In the simplest telling, a singularity is a point where the ordinary rules of physics break down. Density becomes infinite, temperature becomes infinite. Space itself pinches down to something with no size at all. If you follow the expansion of the universe backward in time, running the movie in reverse, all the galaxies rush toward each other, and the fabric of space shrinks. In the simplest models, that shrinking never stops. It keeps going until everything sits inside a point smaller than an atom, smaller than a thought, smaller than any measurement could ever capture. For much of the 20th century, this was the picture many astronomers carried in their heads. The equations of general relativity written by a certain patent clerk turned physicist, seemed to demand it. Trace the expansion back far enough, and you arrive at a moment where the math itself gives up, a place where every quantity becomes infinite at once. Physicists gave this moment a name and a number. They called it T=0, the first tick of the cosmic clock. But even from the start, there was quiet unease about this idea. An infinity in a physics equation is not usually a triumph. It is usually a warning. It tends to mean that the theory being used has reached the edge of what it can describe. The equation is telling you, in its own polite way, that something is missing. General relativity describes gravity beautifully at large scales. It explains the orbits of planets, the bending of starlight, the slow drift of galaxies. But it says nothing about the quantum world. It does not know how to handle particles that behave like waves, or fields that flicker in and out of certainty. When you shrink the universe down to a point, quantum effects become impossible to ignore, and relativity, on its own, has no way to include them. So, the singularity may not be a real place at all. It may simply be the shadow that appears when you use the wrong tool for the job. Trying to describe the earliest instant with pure general relativity might be like trying to measure the temperature of a candle with a ruler. The instrument gives an answer, but the answer means nothing. Some researchers believe the singularity is a genuine feature of nature, an actual boundary where time itself begins. Others suspect it is only a mathematical artifact, a false wall that will dissolve once a deeper theory replaces the old one. That deeper theory would need to combine gravity and quantum mechanics into a single, working whole, and no one has yet built such a theory in a form everyone agrees on. There is a famous argument put forward by one thoughtful mathematician who spent decades studying black holes that adds another layer of doubt. He pointed out that inflation, if it truly happened, would need to begin from an extremely special starting condition. The early universe was not just small, it was also astonishingly smooth and orderly, with very low entropy. Entropy is the measure of disorder, of how many ways the pieces of a system can be arranged. A low entropy start means the universe began in one of the rarest possible configurations. The odds of that happening by chance, if the singularity were truly the beginning, seem vanishingly small. Some see this as a hint that inflation alone cannot be the whole story. Something must have prepared the stage. Others push back. They argue that our sense of what counts as rare or ordinary may not apply at the birth of a universe. There may be selection effects we cannot yet see. There may be deeper principles that make the smooth beginning inevitable rather than lucky. The debate continues in quiet journals and long chalkboards, with no clear winner. If you close your eyes and picture the singularity as the old textbooks drew it, you might see a single glowing point suspended in blackness. But that picture is almost certainly wrong. There was no surrounding blackness for the point to sit in. There was no outside. There may not even have been a point at all. Only a region where our concepts of size and location have no meaning. Beneath the smooth surface of the standard story, the depths grow murky. The singularity may be a real edge, or a mirage produced by incomplete equations, or something stranger still. For tonight, it is enough to notice that even the beginning has a beginning problem, and to let that gentle puzzle carry you a little farther into rest. Rest for a moment with an idea that stretches the mind gently, like slow tide against a shore. What if inflation, once it began, never truly ended everywhere at once? What if it is still going on, right now, in regions of space so far removed from us that we can never see them, never touch them, never learn their names? This is the picture that some cosmologists call eternal inflation. It suggests that the great swelling of space is not a single event with a start and a stop, but an ongoing rhythm, a pulse that continues in some parts of reality while it settles down in others. The seed of this idea lies in the strange behavior of the inflation field, the hypothetical energy field thought to have driven the earliest expansion. Picture that field as a vast invisible ocean spread through space. In most places, this ocean is calm, sloping gently downward toward a lower energy state. When it reaches the bottom, inflation ends in that region, and the leftover energy becomes matter and light. This is what may have happened in our own patch of the universe. But quantum physics does not allow the field to be perfectly smooth. Tiny ripples appear at random, small trembles in the field's value. In some regions, these ripples push the field upward instead of downward, back toward higher energy. Where that happens, inflation continues. Those regions keep expanding at their runaway rate, doubling and doubling in volume, faster than the field can settle. So even as some patches drop out and become quiet, calm cosmoses like our own, the inflating background keeps growing between them. It grows faster than it can be consumed. The endless field outpaces its own endings. This is the rhythm that eternal inflation proposes, a ceaseless breath in which pockets of stillness form inside a larger, ever-expanding restlessness. If the idea is right, our observable universe is one of those quiet pockets, one small bubble of settled space, nestled inside something vastly larger and still churning. And the moment we call the beginning may not be a true beginning at all. It may simply be the moment our particular pocket calmed down. It is a beautiful picture, and it answers some questions elegantly. It suggests why inflation could start at all, since in an eternal setup, it does not need a special first cause. It has, in a sense, always been happening somewhere. But not everyone accepts this view, and the objections are serious. Some physicists point out that eternal inflation depends on extrapolating quantum behavior into regimes we have never tested. The mathematics that works well for small fluctuations may not hold when those fluctuations dominate. The picture of endless bubbles may be an artifact of pushing the equations too far. Others raise a deeper worry. If inflation truly never ends, and if new pockets form forever, then everything possible happens somewhere, an infinite number of times. This creates a puzzle called the measure problem. How can we say what is likely in such a setup when every outcome, no matter how rare, occurs infinitely often? The very notion of probability begins to unravel. Some researchers wonder whether eternal inflation, taken to its full conclusion, actually predicts anything at all. Competing views suggest inflation may end globally rather than locally. In these pictures, the field settles everywhere at roughly the same cosmic moment, and there is no endless background of expansion running on beyond our view. This would restore a cleaner rhythm, a single episode with a definite close, but it would require the inflatant field to behave in a much more orderly way than the simplest quantum models suggest. The evidence to choose between these possibilities does not yet exist. Both remain open. There is something quietly humbling in sitting with this. The cycles we know from ordinary life, the tides, the seasons, the slow turning of galaxies, all have edges we can measure. Eternal inflation, if it is real, has no such edges. It would be a rhythm without a beat we could count, a breath without a chest. Only pockets like ours would ever slow enough to notice themselves. And so the question shifts a little in shape. Instead of asking what came before inflation, we might ask whether there is a before at all, or whether the word only makes sense from inside a settled pocket. The eternal picture invites us to imagine that our beginning is a local event inside something older and stranger, something that may have no first moment in the ordinary sense. Whether this is a true description of reality or a beautiful mathematical dream is one of the softest, most patient questions in all of cosmology. It waits for evidence that may take generations to arrive, or may never arrive at all. If eternal inflation is real, then our universe may not be alone. It may be one small pocket in a much larger sea. Picture a still, dark ocean stretching further than the mind can hold. Now imagine that within this ocean, tiny bubbles keep forming, each one a whole cosmos in its own right. Each bubble carries its own space, its own time, its own quiet history. This picture, strange as it sounds, follows naturally from the math of some inflation models. It is one possible answer to the question of what surrounds our beginning. It is also, importantly, only one possibility among several. In these models, the field that once drove inflation never fully turned off everywhere. In most regions of a vast background space, it kept going, stretching those regions faster than thought. Only in isolated patches did the field slow down and release its energy, forming warm, quiet bubbles of ordinary space. Our whole visible universe, all the galaxies we have ever mapped, may sit inside just one such bubble. Beyond its edge, the wider sea continues to inflate. New bubbles form endlessly. Old bubbles drift apart, carried away by the growing space between them. The strange part is what happens between the bubbles, because the background keeps expanding at such a furious rate. No bubble can ever catch up to another. Two neighboring cosmoses could sit relatively close in the larger sea and still never meet. The space between them stretches faster than any signal can cross. Each bubble becomes a sealed pocket. Each is a cosmos with no window to its neighbors. If this picture is correct, we may have countless siblings we can never see, never touch, never hear from. Some researchers wonder whether two bubbles might, on rare occasions, collide. If our young universe brushed against another bubble long ago, the impact could have left a faint, round bruise in the sky. A gentle, circular pattern in the oldest light might mark the place where two cosmoses once touched. Astronomers have searched for such patterns in the cosmic microwave background, the ancient glow left over from the early universe. So far, nothing clear has turned up. The searches continue, patient and careful, but the sky remains quiet on this question. Not everyone finds the bubble picture convincing. Critics point out that the idea rests on assumptions we cannot test directly. If other bubbles exist forever beyond our reach, in what sense are they real? And in what sense is the claim science at all? Some physicists argue that a theory which predicts endless unseen worlds is barely a theory. Others answer that if the math of inflation naturally produces those worlds, we should take them seriously, even if we can never visit. The debate is deep and honest. It touches the very edge of what physics is allowed to ask. There is a further puzzle inside the bubble picture. If countless pocket universes exist, each may cool into slightly different physics. One bubble might have stronger gravity, another might have particles with different masses. Some might allow stars and planets and slow chemistry. Most, perhaps, would be barren. In this view, our universe looks finely tuned for life, only because we happen to live in one of the rare hospitable pockets. This idea, sometimes called the landscape of possibilities, is one attempt to explain why the constants of nature seem so kind to us. But it is far from proven. Other researchers believe the constants may yet be explained by deeper principles, with no need for a sea of neighbors at all. Even the geometry of the picture is uncertain. Some versions of eternal inflation describe bubbles as roughly round patches inside a stretching background. Others describe endless branches of a self-copying field, with no clear boundaries at all. The images we form in our minds are guides, not photographs. The true structure, if it exists, may be stranger than any image we can draw. What is worth sitting with tonight is the shape of the idea itself. Our beginning may not have been a single event in a single place. It may have been one small flare of stillness inside a wider, endless motion. The moment inflation cooled in our patch may have been an ordinary event, repeated countless times before and countless times after, in regions we will never reach. Or it may have been a rare and precious thing, unique in ways we do not yet grasp. Both possibilities are alive in the science. Both remain open. And out there, if the picture holds, other bubbles may be quietly cooling into their own long stories, their own slow galaxies, their own dark and gentle nights. Some ideas in cosmology reach so far into extremes that they bend the mind gently, like a slow current pulling a leaf downstream. The bounce is one of those ideas. It asks us to imagine that our universe did not begin at all, at least not in the way we usually picture beginnings. It asks us to picture, instead, a universe that shrank before it grew, a universe that fell inward across unimaginable depths of time, reached a smallest possible size, and then rebounded outward into the expansion we now measure. If this picture is right, then what came before inflation was not nothing. It was another universe, or another phase of this one, collapsing toward a floor it could not pass through. And that floor sits at one of the most extreme edges physics has ever tried to describe, at densities so high that a single teaspoon of matter would weigh more than every star in every galaxy we can see, at temperatures so hot that the very idea of temperature begins to lose meaning, at curvatures of space so tight that geometry itself would fold in on itself like paper crushed inside a closed fist. Classical physics predicts that such a collapse would end in a singularity, a point of infinite density where the equations simply break. Some researchers wonder whether quantum effects step in long before that limit. In-loop quantum cosmology, one proposal for merging quantum theory with gravity. Space is not smooth at the tiniest scales. It has a grain of finest possible weave, like a fabric that cannot be cut any thinner. When matter tries to collapse below that grain, the theory suggests something remarkable happens. Gravity flips its sign, attraction becomes repulsion, and the collapse bounces. The numbers involved sit at the far end of every scale we have. The bounce, if it happens, would occur near the Planck density, around 10 to the 93rd grams per cubic centimeter. That number is so large, it does not really describe anything a human can hold in mind. It is the density where the smooth picture of space and time stops working entirely. It is the deepest floor physics has ever guessed at, and no experiment has ever reached anywhere close to it. Above that floor, in the theory, the universe would have been the mirror image of ours, a contracting cosmos, cooling as it fell inward, then heating violently at the turnaround, then unfolding into the hot, dense state we associate with the earliest moments after inflation. Some versions of the model suggest that inflation itself could begin naturally on the far side of the bounce, driven by leftover energy from the crunch. In that picture, the strange smoothness we see in the sky today would be inherited in part from a previous cosmos that combed itself flat as it fell. Not everyone finds this convincing. A competing view holds that quantum gravity effects may not save us from a singularity at all. In this reading, the classical prediction stands, and the universe truly begins at a moment where time itself has an edge. The bounce, in that case, is a mathematical convenience, a way to avoid a painful boundary that may in fact be real. Between these two views sits a quiet uncertainty. We have no direct observation of the pre-inflationary state. We have no experiment that can reach Planck scale densities. We have only equations and their disagreements. There are subtler extremes in the bounce idea as well. If a bounce occurred, the universe on the other side would have been enormously old before it began contracting. Older, perhaps, than any time scale our instruments can probe. Some cyclic versions of the theory imagine bounce after bounce, stretching back across durations that dwarf the current age of the cosmos by factors we cannot easily name. Other versions suggest only one bounce, a single hinge between two epochs. The models diverge sharply, and none has yet found evidence to settle the disagreement. What makes the idea sit strangely in the mind is the reversal of intuition it requires. We are used to thinking of the beginning as the smallest moment, the youngest instant, the seed from which everything grew. The bounce asks us to picture the beginning as a turning point instead, a pivot, a lowest note in a longer song whose earlier verses may be forever hidden from us. Whether that song exists, or whether our universe simply began without any prior verse at all, remains an open question. The extremes of density and curvature that would decide it lie far beyond any laboratory we can build. For now, the bounce remains one possibility among several, a quiet candidate for what came before the great unfolding. Rest for a moment with the idea of rhythm, a pulse, a breath in, a breath out. Some cosmologists have wondered whether the universe itself might follow a pattern like this, stretching and contracting across spans of time, so vast that our whole recorded history would not fill a single tick of the clock. These are the cyclic cosmologies, and they carry small, quiet details that even most curious readers never hear about. The oldest versions of the cyclic idea go back nearly a century. In the 1930s, a physicist named Richard Tolman worked out what would happen if a universe expanded, slowed, fell back, and bounced. He found a problem so subtle it feels almost like a whisper. Each cycle, he calculated, would carry a little more disorder into the next. Radiation would build up. The bounces would grow longer and larger. Any universe playing this game forever would have started in a state of impossible order, or it would already be too worn out to bounce again. That single quiet objection shaped decades of thinking. Modern cyclic theories try to answer Tolman gently. Some propose that the universe stretches so far during its expansion phase that everything thins out to almost nothing before the next contraction begins. The disorder does not vanish. It just spreads across a volume so enormous that, from the point of view of any small region, the slate feels clean. Whether this really counts as a fresh start is a question researchers still argue about in small, careful papers, filled with equations most of us will never read. These theories live details that feel almost tender. The moment of the bounce, if it happens, might last less than a trillionth of a second in the reckoning of the fields involved. Yet in that flicker, the whole geometry of space would flip through a state so strange that our usual ideas of distance and duration stop making sense. Some models suggest the bounce leaves faint ripples, gentle patterns in the density of matter, that a future telescope might one day tease out of the sky. There is also the small, beautiful notion of a scale factor, a number that describes how large space is at any moment. In an ordinary expanding universe, that number grows. In a cyclic universe, it rises and falls like the tide. Researchers who spend their careers with these equations sometimes speak of the scale factor with real affection, as if it were the heartbeat of a living thing. Another quiet detail lives in the entropy problem itself. The physicist Roger Penrose has argued, patiently and for many years, that the smoothness of our early universe demands an explanation no ordinary cycle can give. His own idea, called conformal cyclic cosmology, proposes that when the universe grows old enough, when every black hole is evaporated and every particle has drifted into isolation, the very meaning of size fades away. A cold, empty, endless universe becomes mathematically indistinguishable from a hot, dense, tiny one. The end of one eon quietly becomes the beginning of the next. It is a strange and lovely idea, and it remains, for now, a minority view. Not everyone finds these rhythms convincing. Many researchers point out that cyclic models still need to explain why the bounce happens at all. What physics allows a contracting universe to turn around instead of collapsing into a point? The equations of general relativity, taken at face value, do not permit such a turnaround. Something new must step in at the smaller scales. That something might be quantum gravity, or extra dimensions, or a repulsive form of energy that only wakes up under extreme pressure. Each candidate carries its own uncertainties, and none has been tested. A competing view holds that the universe simply began, once in some fashion we do not yet grasp, and that the search for endless cycles is a kind of poetry rather than physics. Both camps agree on one thing, though. The pre-inflationary state, whatever it was, cannot be reached by our telescopes directly. We can only listen for its echoes in the faint patterns of the sky, and in the internal consistency of our equations. There is something restful in sitting with these small details, the bounces that may or may not have happened, the scale factor rising and falling like breath, the entropy that either resets or slowly accumulates across ages we cannot count. None of it is settled. Each idea is a quiet room in a much larger house, and researchers are still walking through those rooms, tapping the walls, listening for what might lie behind them. For tonight, it is enough to know the rooms are there, and that someone is still patiently listening. Around the turn of the millennium, a small group of theorists began asking a strange and quiet question. What if the universe did not begin hot, but cold? What if the fire we call the Big Bang was not the true beginning at all, but only a later moment in a much longer and stranger story? Out of that question came an idea called the Ekpyrotic model, a name borrowed from an old Greek word meaning something like conflagration, or born from fire. The people behind it were physicists working at Princeton and Cambridge, and a few other places trying to bend the standard picture of inflation into a new shape. The idea took form around the year 2001. A cosmologist named Paul Steinhardt, along with Neil Turok, Justin Khoury, and Bert Overath, sketched a picture very different from the usual one. In the usual picture, the universe starts blindingly hot and dense, and inflation stretches it smooth. In their picture, the universe begins slow, cold, nearly empty, and almost perfectly still. All the smoothness we see in the sky came from that long, quiet preparation, not from a sudden burst of expansion. The strange thing is that Steinhardt himself had been one of the founding architects of inflation years before. He had helped build the very idea he was now trying to move beyond. That change of heart is part of what makes the history so interesting. It was not an outsider throwing stones at a settled theory. It was one of the theory's own parents wondering, quietly, if there might be another way. The Ekpyrotic idea grew out of a branch of physics called string theory, which pictures the smallest pieces of reality as tiny vibrating threads. In some versions of that theory, our whole universe sits on a kind of vast membrane, called a brane for short, floating inside a higher dimensional space. The Ekpyrotic model imagined a second brain, drifting slowly toward ours, across that hidden extra dimension. When the two brains finally touched, the collision released the flood of heat and light we now remember as the Big Bang. Before that touch, though, everything was cold. That is the piece that mattered most for our question tonight. The pre-inflationary state in this picture was not a fever of energy or a wild quantum foam. It was a long, dim, patient stretch of near nothingness, gently smoothing itself over enormous spans of time. The universe did not need a sudden explosion to look smooth. It only needed to wait. Of course, none of this is proven. It is one attempt among many to imagine what came before the beginning we know. Critics have raised many objections. The mathematics of two brains colliding is delicate and hard to control. The predictions for the tiny ripples in the cosmic microwave background do not always match observations as cleanly as inflation's predictions do. Some physicists feel the model quietly imports the same puzzles it was meant to solve, only pushing them one step further back. The debate has never fully settled. Still, the Ekpyrotic proposal changed the conversation. It reminded everyone that inflation, for all its successes, is not the only story that fits the data. It opened a door to cyclic thinking, to the possibility that the Big Bang was one event in a much older rhythm, and it forced cosmologists to look again at what they meant when they said the universe began. The tools used to test these ideas are strange and beautiful: telescopes in high deserts, balloons drifting above Antarctica, satellites parked far from Earth, all listening for the faintest whisper of ancient light. Different theories predict slightly different patterns in that light. Inflation tends to predict a certain balance of gentle ripples and long, slow waves in space itself. The Ekpyrotic idea tends to predict something a little quieter, with fewer of those long gravitational waves. So far, no measurement has been sharp enough to fully decide between them. That is the strange and lovely place we sit in tonight. Two competing pictures of the deep past, both consistent with what we can see so far, both waiting for better instruments and clearer skies. One says the universe began hot and stretched smooth by inflation. The other says it began cold and was smoothed by long, patient drift, then set alight by collision in an unseen dimension. Neither picture is confirmed, neither is dismissed. The people who first proposed the cold beginning did not claim to have solved the mystery. They only offered another way of imagining it, another gentle path back toward that first moment. And somewhere in the archives of ongoing measurements, the answer may already be quietly hiding, waiting for us to learn how to read it. There is an idea in modern physics that sounds more like a dream than a theory. It suggests that the universe we live in is not the only kind of space that exists. Our whole cosmos, with its stars and galaxies and dark stretches between them, might sit on a thin sheet. That sheet is called a brane, and the brane may float inside a larger space with more dimensions than we can see. This picture comes from string theory, which is itself one of the most debated ideas in physics. In string theory, tiny vibrating strings replace the point particles we usually imagine. For the math to work, these strings need more room to move than the 3 dimensions of space we know. Some versions call for 10 dimensions, others call for 11. The extra ones are thought to be curled up too small to notice, or stretched out into a vast hidden region we cannot enter. Within that hidden region, our universe might be one of many branes. Think of two enormous flat sheets floating in a dark, higher dimensional room. Each sheet holds its own physics, its own particles, its own light. Neither sheet can see the other. But gravity in this picture might leak between them. That is one reason gravity feels so weak compared to the other forces we know. The strange part comes next. Some cosmologists have wondered whether these branes could drift toward each other very slowly across the higher dimensional space. And if two branes ever touched, the collision would release an enormous burst of energy. That energy would fill the touching sheets with hot, dense matter. It would look, from inside the brane, exactly like a Big Bang. This is the heart of the Ekpyrotic and Cyclic brane models. In these pictures, what we call the beginning of our universe was not really a beginning at all. It was a meeting. Two sheets of space came together, filled the void between them with heat and light, and then drifted apart again. In some versions, this happens once, in others it happens over and over, with each collision setting a new cosmic clock ticking. What makes this idea so surprising is that it offers an alternative to inflation itself. In the standard picture, a tiny patch of space blew up unimaginably fast, smoothing everything out. In the brane collision picture, the smoothness comes from a slow, careful approach of the two sheets over long ages before they touched. There is no sudden burst of expansion. The heat and structure we see arise from geometry meeting geometry. Whether any of this is true remains completely open. String theory has not been tested in a laboratory. No experiment has yet found evidence of extra dimensions. The branes, if they exist, would be far too large and far too separated for us to detect directly. Some physicists find the mathematics beautiful and full of promise. Others are deeply skeptical, arguing that a theory which cannot yet be tested is not really a theory of nature, but a very elegant guess. There is also a quieter puzzle inside the brane idea. If two sheets can collide to make a universe, what set them drifting in the first place? What decided their shape, their spacing, the strength of their pull toward each other? The mystery of what came before inflation simply moves one level deeper. Instead of asking what came before the hot, dense state, we now ask what came before the branes met. The question does not disappear, it only changes clothes. Still, there is something soothing about picturing it. Imagine a vast dark space with two soft luminous sheets floating in it. They move so slowly that 1 trillion years would barely count as motion. Their surfaces ripple gently. On one of those surfaces, if the theory is right, sits everything you have ever known. Every ocean, every mountain, every sleeping city, every star you have ever looked up at. All of it painted onto a thin membrane in a larger room we cannot enter. Whether this room is real, or whether it is only a lovely story the mathematics likes to tell, no one can say yet. The inflation picture and the brane collision picture make some slightly different predictions about the patterns left in the ancient light of the cosmos. Careful measurements may one day favor one over the other, or the measurements may stay too subtle to decide, and both ideas may remain on the table for a long time. For now, the brane picture stands as one of the strangest and gentlest guesses about what came before. It says the beginning may have been a touch, two silent sheets, meeting once in the dark and giving rise to everything. There is an idea in cosmology, so gentle in shape that it almost feels like a piece of geometry from a dream. It came from two thoughtful physicists working together, wondering what would happen if the universe had no starting edge at all. Not a bang, not a boundary, not a first tick of a clock, just a smooth, rounded beginning where time itself softens into space. This is the no-boundary proposal, and it connects the question of what came before inflation to the deeper question of whether before is even the right word. Picture the surface of a globe. If you place your finger at the South Pole and walk in any direction, you always move north. There is no south of south. The pole is a real place, but no direction points beyond it. The no-boundary idea imagines the beginning of the universe as something like that pole. Time, near the very start, curves into another dimension of space, and so asking what came before the beginning becomes a bit like asking what is south of the South Pole. The question has a shape, but the shape closes on itself. This idea does not stand alone. It reaches across physics and connects to many other systems that shape how we think about the cosmos. It draws on quantum mechanics, which allows tiny things to exist in blurred states of possibility. It draws on general relativity, which lets space and time bend and stretch. And it draws on the mathematics of imaginary numbers, which sound strange, but are a normal tool in physics. When you weave these threads together, you get a picture where the universe emerges without ever needing an outside cause. It simply is, and its beginning is a soft curve rather than a sharp corner. The no-boundary proposal touches the inflation story in a very specific way. If it is right, then the tiny patch of space that would later inflate did not need to be handed to us by some earlier phase. It emerged smoothly from a rounded quantum region where time behaved like another direction of space. Once time settled into its familiar role, inflation could begin, stretching that quiet patch into the vast cosmos we see. In this picture, the pre-inflationary state is not a place or a moment. It is a geometry that closes gently on itself, like the bottom of a bowl. Not everyone agrees. A competing view, often linked to another careful thinker in the same field, imagines the universe tunneling into existence from a state of pure nothing. In this tunneling picture, there is a kind of quantum leap, a jump from no space and no time into a small, expanding bubble that then inflates. Both ideas try to describe how a universe could arise without a prior universe. Both use similar mathematics, but they disagree on which quantum paths matter most, and they can predict different starting conditions. The debate has run for decades, and it is still unsettled. There is also a quieter disagreement about what the no-boundary proposal actually predicts. Some careful re-examinations have suggested that when you apply the mathematics more strictly, the smooth beginning might favor universes that are wild and uneven, rather than calm and orderly. Other researchers push back and argue that the original picture still holds when you choose the right way to sum over possibilities. The question of which calculation is correct remains open, and it matters, because it decides whether this beautiful idea actually matches the smooth universe we observe. What makes the no-boundary proposal feel like a symphony section is how many parts of physics it asks to play together. Quantum theory, gravity, geometry, and thermodynamics all have to agree on the same soft opening note. If any one of them plays out of tune, the picture falls apart. And this is why the idea remains a proposal rather than an accepted answer. We do not yet have a full theory of quantum gravity, the deeper framework that would tell us how space and time behave at the smallest scales. Without that, every model of the cosmic beginning is a sketch drawn in the margins of a larger book we have not finished writing. Still, there is something restful in the shape of the no-boundary idea. It suggests that the universe may not meet a cause in the ordinary sense. It may simply be a closed, self-contained thing whose earliest moments curve away from the language of before and after. Whether that is truly how our cosmos began, or whether some rival picture will one day replace it, is a question no one can yet answer. The mathematics is elegant, the evidence is thin, and the mystery, for now, remains open. Our picture of empty space has been changing for a long time. Once, people thought space was a smooth stage on which the universe played out. Then Einstein taught us that space itself can stretch and curve. And now, in the quiet workrooms of theoretical physics, a new picture has been slowly taking shape. In this newer view, space may not be smooth at all. It may be woven. The idea comes from a field called loop quantum gravity. Its name sounds heavy, but the picture behind it is gentle. Imagine that space, if you could look closely enough, is not a smooth sheet, but a fine mesh. Tiny loops link into other tiny loops, and the pattern of their linking is what we experience as distance, volume, and shape. Zoom out, and the mesh looks smooth. Zoom in, past atoms, past nuclei, past anything a telescope could ever hope to see, and the weave begins to show. This picture has grown slowly over decades in a quiet corner of physics. It has never been the loudest theory in the room. String theory has often received more attention, but loop quantum gravity has kept working, patient and steady, asking a simple question. What if space itself has a smallest piece, not made of matter, but made of geometry, a tiniest possible stitch in the fabric? If that is true, then something interesting happens near the beginning. In the standard picture, if you rewind the expansion of the universe far enough, everything crushes into a single point of infinite density. But a woven space cannot crush that far. The threads can only pack so tightly. At some point the mesh reaches its limit, and instead of collapsing to nothing, it pushes back. This idea is called the Big Bounce. In loop quantum cosmology, the version of the theory that studies the early universe, the moment before inflation was not a singularity at all. It was a rebound. A previous universe, or a previous phase of this one, was contracting it. It grew smaller and hotter and denser, until the woven quality of space refused to compress any further. Then it sprang outward, and that outward spring may have been what set the stage for inflation to begin. It is a soothing picture in its way. No sharp edge, no moment where the equations simply break. Instead, a smooth transition from one state to another, a gentle turning point at the base of time. But we must sit carefully with this image, because it is a proposal, not a proven history. The mathematics of loop quantum gravity is still being worked out. The full theory is not yet complete, and it competes with other ideas, each of which draws the pre-inflationary moment in a different way. The standard singularity view, for instance, still holds much of the field. In that view, the equations of general relativity really do run all the way down to a point, and the strangeness there is a signal that a deeper theory is needed, not a hint that space is woven. String theorists offer yet another sketch, one where the fundamental things are not loops of geometry, but tiny vibrating threads of energy, living in more dimensions than we can see. Each picture makes different predictions. Each remains open. What is quietly changing right now is the willingness of physicists to take these once strange proposals seriously. A few decades ago, asking what came before the beginning was almost a forbidden question. Today, it is a working research topic, with journals and conferences and slow, careful papers. The change has been gradual, like the shifting of a coastline, but it is real. Even more slowly, the tools to test these ideas are also changing. Loop quantum cosmology predicts small specific patterns that a bounce might have left behind in the oldest light we can see, the faint glow from the young universe. Those patterns would be subtle, tucked into the largest features of the sky. Current maps are not quite sharp enough to say if the patterns are there. Future ones may be, or they may not, and the picture will need to shift again. For tonight, though, it is enough to hold the image in mind. A woven space, too finely stitched to tear, a universe that did not begin at a point, but at a bounce. A previous phase, unknown and unknowable, folding smoothly into ours, one theory among several. A quiet possibility, offered gently, and still very much open. The threads of space, if they exist, are far smaller than anything we can measure, and whether they truly weave the void, or whether the void has some other secret shape entirely, remains one of the softest, deepest questions we know how to ask. String theory begins, in a way, with light. Long before the theory tried to describe the first moment of the universe, it started as an attempt to understand how tiny things vibrate, how energy travels, how the smallest possible pieces of reality hum with motion. In this picture, every particle we know is really a tiny loop or thread, so small that no instrument could ever see it directly. Each thread vibrates at its own pitch, and those pitches decide whether the thread appears as an electron, a photon, or something stranger. If the idea is right, then even light itself is a kind of song, sung by a vanishing thread of energy. That image becomes gentle and dreamlike when we try to apply it to the very first moment. In string theory, there is no true point of zero size. The smallest meaningful length is roughly the length of a string, and below that, the ideas of position and distance begin to lose their meaning. A universe that shrinks all the way down to nothing would run into this flaw and stop. So some versions of string theory suggest that whatever came before inflation was not a point of infinite crushing, but a soft, glowing minimum, warm with the light of countless vibrating threads. Picture that state for a moment, a tiny region no smaller than the string scale, humming with every possible mode of vibration at once. In some models, this early state shines with a strange, even light spread through every direction, not the yellow light of a star, not the red glow of hot iron, but a light that comes from the very fabric of space, from the trembling of the threads themselves. It is a light no eye could see, because there were no eyes, and no atoms, and no photons in the familiar sense yet, only the raw song of geometry. From this soft, luminous state, one family of string ideas imagines inflation beginning as a kind of stretching of the extra dimensions. String theory tends to require more than the 3 dimensions of space we know. The extra ones are usually curled up so tightly that we never notice them, hidden in shapes so small that light itself is far too large to explore them. Some researchers wonder whether the way those hidden dimensions settled into their shapes was what set the inflaton field in motion. If so, the pre-inflationary state was not simple at all. It was a knotted, folded thing, quietly choosing its final shape, and that choice lit the fuse. Other string models push in a different direction. They suggest that the pre-inflationary universe was not a single tiny hum, but a broad landscape of possible vacua, each with its own laws, each glowing with a slightly different flavor of light. In this view, our inflation began when one region tunneled from a higher energy vacuum into a lower one, releasing energy the way a warm cloud releases rain. The old vacuum still exists somewhere, according to this picture, still shining with its own quiet light in regions we can never visit. Neither version has been confirmed. String theory remains a set of mathematical ideas without direct experimental proof. The strings themselves are far too small to see, and the extra dimensions, if they exist, are curled far too tightly to probe with any instrument we can imagine building soon. Some physicists find the framework beautiful and promising. Others wonder whether it can ever be tested, and whether a theory that cannot be tested is really a scientific theory at all. That debate is still very much alive. What draws people back to the idea, again and again, is the way it treats the first moment with a kind of tenderness. Instead of a violent point of infinite density, string theory offers a soft floor instead of a naked singularity, a warm minimum. Instead of a hard edge to time, a gentle threshold where the usual notions of before and after begin to blur into something more like a musical rest. The light in this picture is not a burst, but a long-held note. Whether any of this is true, we cannot yet say. The equations are complex, the possible solutions are vast, and the observational clues are faint. Perhaps a careful reading of the cosmic microwave background will one day whisper back some faint confirmation, or perhaps some other pattern in the sky will point elsewhere entirely. For tonight, it is enough to picture that soft, luminous beginning, a quiet floor beneath time, a hum where the loudest bang was supposed to be, a first light that may or may not have shone, waiting for someone, someday, to hear it. If space were a room we could sit in, and if our ears could hear what instruments only measure, the universe would not be silent. It would hum. Radio telescopes catch the whisper of hydrogen drifting between stars. Spacecraft turn the solar wind into a soft, low hiss. The rings of gas around distant black holes ring like slow, deep bells, so slow that a single note takes millions of years to complete. And underneath all of that, if we could tune our hearing far enough down, there is a background rumble left over from the earliest moments after inflation itself. The universe has a voice. It is just a voice, pitched below anything a human ear was built to hear. That quiet, endless hum is a useful thing to hold in mind while we sit with tonight's idea, because one of the strangest possible answers to the question of what came before inflation is that inflation never truly stopped. It only stopped here, somewhere else, in regions of space far beyond anything we could ever see. The same expansion is still going on. New pockets keep forming inside it, and each pocket, when its own inflation ends, becomes what looks, from the inside, like a whole universe. Ours might be only one of them. The picture is called the Multiverse, and it is one possible answer to why our beginning looked the way it did. The idea grows out of something called eternal inflation. In this picture, the inflattened field, the strange hypothetical energy that drove the first burst of expansion, does not switch off cleanly everywhere at once. In some regions, it decays into ordinary matter and light. That is what happened in our part of space, and it gave us stars, planets, and quiet nights. But in other regions, quantum jitters keep the field high. Those regions keep inflating, and inside them, new bubbles keep forming, over and over, without end. Each bubble is its own soft pocket of calm inside a larger, roaring sea that never stops growing. If that picture is right, then the question of what came before our inflation has a gentle answer. What came before was more inflation, and before that, more inflation still. The process is older than our universe, older than our sense of time, perhaps without any true beginning at all. Our pocket is one soft chime inside an endless bell. Some cosmologists find this idea beautiful because it removes the sharp problem of a single, arbitrary starting moment. Others find it troubling for exactly the same reason. If every possible pocket universe exists somewhere, then almost anything can be explained by saying, we happen to live in the pocket where things came out this way. That kind of reasoning is hard to test. Critics wonder whether the multiverse is really a scientific answer at all, or a very well-dressed shrug. The debate is honest, and it is not settled. There are competing pictures, and it is worth pausing with them. Some researchers prefer models where inflation happened only once, in one place, and the initial conditions were fixed by some deeper law we have not yet found. In that view, there is no sea of other bubbles. There is only our universe, and the search is for the rule that made ours the way it is. Others suspect the multiverse exists but takes a very different shape, not bubbles inside eternal inflation, but separate solutions of a deeper theory, each with its own physics sitting side by side, in a mathematical sense rather than a spatial one. And still others suspect that the whole idea will look, a century from now, like a useful step towards something we cannot yet imagine. If the multiverse is real, the sound of it, in some poetic sense, would be layered. Each bubble would carry its own quiet hum, its own leftover echo from its own inflation. Ours has been measured, a faint microwave glow, filling every direction of the sky, the cooled voice of our own beginning. Whether other bubbles carry other glows, with other patterns, other tones, other kinds of matter singing inside them, is something we may never be able to hear. The walls between bubbles, if they exist, may be forever beyond our reach, and so we sit with a strange, gentle possibility that our universe is a single soft note inside a larger music we cannot listen to. That inflation, rather than beginning once, may still be going on somewhere, quietly making new rooms. It is only one answer among several. The evidence is thin, the question is still wide open, but it is a lovely thing to wonder about while the night grows deep around you. The oldest light we can see is a soft, even glow that fills the entire sky. We call it the cosmic microwave background. It reaches us from every direction, faint and cold, only a few degrees above the coldest temperature possible. This gentle bath of radiation is a snapshot of the universe when it was about 380,000 years old. Before that moment, the cosmos was too hot and too dense for light to travel freely. After that moment, the fog lifted, and the first light streamed out across the growing sky. That light carries numbers, beautiful, patient numbers. When we measure the temperature of the microwave background across the sky, we find it is almost the same everywhere, to about 1 part in 100,000. That is an astonishing evenness. Take a bowl of water and measure it to 5 decimal places, and you would still find more variation than the early universe shows across billions of light years. And yet, within that smoothness, there are tiny ripples, slightly warmer spots, slightly cooler ones, and it is in those ripples that the mathematics begins to sing. Cosmologists take a map of these temperature variations and break it into waves. This is a bit like listening to a chord and picking out each note inside it. The math they use is called a power spectrum, and it tells us how much of the pattern lives at each size on the sky. When you draw the spectrum out, it forms a graceful curve with a series of gentle peaks and valleys. Those peaks are the fingerprints of sound waves that rolled through the young cosmos. Waves of hot plasma sloshing under the pull of gravity. Inflation, if it happened, should have set the stage for all of this. The theory predicts that quantum ripples, born small enough to fit inside an atom, were stretched to enormous size by the sudden expansion. Those stretched ripples became the seeds of the peaks we now measure, And when the numbers came in from satellites orbiting far above the Earth, they matched the predictions of inflation remarkably well. A near-perfect flatness, a near-perfect smoothness, a gentle tilt in the spectrum that inflation had guessed at years before the data arrived. Still, the story is not tidy. On the very largest scales, where we look at patches of sky wider than about 60 degrees across, the microwave background is quieter than the simplest inflation models expect. There is less signal at the biggest sizes than the math predicts. This is sometimes called the low quadrupole anomaly, and no one is sure what it means. It could be a statistical fluke, a coincidence in the one universe we happen to inhabit, or it could be a whisper from before inflation began. Some researchers wonder if the pre-inflationary state, whatever it was, left a faint scar at the largest angular scales, if inflation started from a bounce, or from a quantum tunneling event, or from some other unknown beginning. The earliest ripples might carry a signature of that origin. Those earliest ripples would be the ones we see today at the widest sweep of the sky. A cyclic model might leave one kind of imprint. A loop quantum cosmology bounce might leave another. Eternal inflation might leave a third. And the plain, simple version, where inflation runs long enough to erase everything before it, would leave none at all. The trouble is that at these largest scales, we are limited by cosmic variance. There is only one sky. We cannot rerun the experiment. When you have just a handful of patches to measure, the numbers wobble no matter what the underlying theory says. It is like trying to guess the weather of an entire planet from one afternoon in one meadow. The math is exquisite. The sample is small. There are ratios in this data that are known to remarkable precision. The universe is flat to within about 0.5%. The ratio of ordinary matter to dark matter falls near 1 to 5. The age of the cosmos comes in near 13.8 billion years, calculated from the geometry of these tiny ripples. These are elegant, hard-won numbers, and yet, when we push them backwards, past the surface of last scattering, past the reheating that ended inflation, we run into the war of the unknown. The cosmic microwave background might remember something older than itself. It might not. The equations that describe it are clean and lovely. The story they tell about the very first moment is still unfinished. Somewhere in those faint patterns of warm and cool, the answer to what came before may be hiding, quietly waiting for a set of eyes patient enough to read it. If any traces of the pre-inflationary state survived at all, they would be the most delicate fossils in the universe. Imagine a footprint left in soft ash, then buried under mountains of stone, then stretched across billions of light years. That is roughly what physicists are searching for when they look for hints of what came before inflation. The signal, if it exists, is fragile beyond anything else we try to measure, and the balance required for it to still be readable today is almost impossibly fine. Inflation, by its nature, erases things. It takes any small region of space and stretches it until every wrinkle, every bump, every uneven patch gets smoothed out. That is part of why the observable universe looks so uniform. But this same smoothing power is what makes the pre-inflationary state so hard to study. If inflation lasted even a little longer than the minimum needed, any fossil of what came before would be diluted past the point of detection. The window in which those traces could still show themselves is razor thin. Some researchers wonder whether the very largest features in the cosmic microwave background, the faint glow left from the young universe, might carry these traces. At the biggest angular scales, the ones that stretch across nearly the whole sky, There are hints of gentle anomalies. A slight lack of power in the largest ripples. A faint alignment of certain patterns. These oddities may mean nothing. They may be simple statistical accidents in a universe with only one sky to measure. But one possibility is that they are the last whispers of a phase before inflation began, preserved only because inflation ended just soon enough to leave them barely visible. The balance here is truly fragile. If inflation had gone on for even a few extra doublings of size, those largest patterns would have been pushed beyond our horizon, out where we can never see. If inflation had stopped a little earlier, the universe would not look as smooth and flat as it does. The narrow band that allows both a smooth universe and possible fossils of what came before is a strange coincidence, or a deep clue, depending on which theorist you ask. Other researchers argue that no such fossils could survive at all. In their view, inflation is too effective an eraser. Whatever came before is gone in principle, not just gone in practice. The largest anomalies in the microwave sky, they suggest, are almost certainly just noise. This is a competing view worth sitting with. It says the pre-inflationary state may be forever beyond reach, not because our telescopes are too weak, but because the physics itself hides the record. Then there is a third camp, working in loop quantum cosmology and related ideas. They calculate what a quantum bounce before inflation might leave behind. In some of their models, the bounce imprints a soft ringing on the largest scales, a kind of low bass note in the cosmic background. If real, this would be an echo of the moment when a contracting universe rebounded into an expanding one. The predictions differ from model to model, and the signal, if any, sits right at the edge of what current instruments can measure. The evidence is incomplete, and honest researchers say so. What makes this whole search feel so delicate is how many variables must line up. The strength of inflation, its exact duration, the properties of the inflaton field, whose true nature we still do not know. The details of whatever preceded it. Change any one of these by a small amount, and the sky we see would look different, or the fossils would vanish, or the universe would never have formed structures like galaxies at all. The conditions that make our cosmos both smooth and richly detailed sit on a narrow ledge, and no one yet knows why the ledge is where it is. Some find this fine-tuning suspicious and take it as a sign that a deeper theory is missing. Others see it as evidence for a vast multiverse, where every possible balance is tried somewhere, and we simply live in one of the rare places where structure formed. Both views remain open, and neither has been confirmed. The fossils, if they exist, might one day help decide between them, or they might stay silent forever, buried too deep under the stretch of inflation. For tonight, it is enough to picture that faint glow across the whole sky, and to imagine that somewhere in its softest patterns, a memory of the world before might still be resting, very quiet, very old, waiting to be noticed, or waiting to be finally dismissed as nothing at all. Time has a direction. We feel it every moment. Cups fall and shatter, and we never see the pieces gather themselves back into a cup. Ice melts in warm tea and does not refreeze. Stars burn their fuel and grow old. This one-way flow, from ordered to disordered, is what physicists call the arrow of time. It points from past to future, and it seems to point that way everywhere we look. Yet, the deep laws of physics do not require this direction. Most of the equations that describe motion and force work equally well running forward or backward. A ball rolling down a hill, played in reverse, is still a valid solution to the math. The arrow then does not come from the laws themselves. It comes from the way the universe began. It comes from the fact that our cosmos started in a state of astonishingly low disorder and has been slowly unwinding toward higher disorder ever since. Which brings us to a quiet puzzle at the heart of tonight's question. If the arrow of time points away from the low disorder beginning, what did that arrow look like before inflation started? Was there an arrow at all? Was there a before? Some thinkers argue that time itself only becomes meaningful once space, energy, and change exist in familiar forms before inflation. If the universe was a shimmering quantum haze, with no stable clocks, no stable particles, no stable anything, then the word before may not describe a real moment. It may only describe our need to keep asking. In this view, time emerges from deeper physics, the way heat emerges from the jostling of countless atoms. Take away the atoms, and heat has no meaning. Take away the classical universe, and time may have no meaning either. Others push back. They say the arrow of time must come from somewhere, and pushing the question into a quantum fog does not answer it. It only hides it. If the universe truly began in a state of low disorder, something had to set that state. Was it chosen? Was it random? Was it the only state possible? These are open questions, and honest researchers admit they do not know. One influential line of thought suggests that the low disorder start was extraordinarily unlikely. Out of all the ways a young universe could have been arranged, only a tiny sliver of arrangements would allow the smooth, expanding, structured cosmos we see today. Why did our universe pick that sliver? One answer is that we simply live in a rare bubble where the numbers worked out and countless other regions did not. Another answer is that some unknown principle forced the beginning to be smooth. A third answer is that the question is malformed, and asking why the beginning was special is like asking why north is north. Some cosmologists wonder if the arrow of time might have pointed the other way on the far side of the beginning. Picture two arrows leaving a single moment, back to back, each one racing outward into its own version of a future. In one direction, our universe unfolds. In the other, a mirror universe unfolds with its own galaxies and its own quiet observers, who also feel time flow forward, away from the shared origin. Neither side is the past of the other. Both are futures. If this idea holds, the question of what came before inflation dissolves, because there was no before. There were only two forwards. Other researchers find this picture too clean. They point out that we have no direct evidence for a mirror side. We may never have any. The idea is beautiful, but beauty is not proof, and so it sits on the shelf of possibilities, alongside quantum bounces and no boundary proposals and eternal inflation, waiting for some observation that might tip the balance. What makes this puzzle so gentle to sit with is that it may never be solved by measurement alone. The arrow of time before time is not something we can point a telescope at. It lives in the logic of the beginning, in the mathematics of initial conditions, in questions about whether cause and effect even apply, when there is no yet or already. Some physicists suspect this is a genuine limit of science. Others suspect we simply have not found the right framework, and that a future theory will make the answer feel obvious in hindsight, the way roundness feels obvious once you leave the ground. For now, the arrow points where it points. We remember the past and wonder about the future, and somewhere behind us, past the wall of inflation, the direction of time itself becomes a soft, unresolved question, waiting quietly for someone to ask it in a new way. One of the deepest puzzles about the early universe is how it began so evenly. When we look out at the oldest light we can see, the glow left over from just after the hot beginning, it looks nearly the same in every direction. The temperature of that ancient light varies by only a tiny fraction across the whole sky. That smoothness is strange, left to itself. A young universe should have been lumpy, chaotic, wildly different from one patch to the next. Inflation offers one answer. If a tiny region stretched by an enormous factor in a fraction of a second, then whatever tiny differences existed inside that region would have been ironed out, smeared thin across the whole sky. What we see as smoothness on huge scales today would simply be the memory of a much smaller, calmer patch that got blown up to become everything we can observe. That answer is elegant, but it hides a deeper question. Why was that starting patch so smooth to begin with? Inflation does not create the calm, it only spreads it. Something had to prepare the ground. Some pre-inflationary state had to be quiet enough, ordered enough, for inflation to grab hold and stretch it into a sky. Looking forward across the long future of cosmology, this is the question many researchers hope to answer. In 1,000,000 years, the sky will look almost the same to human eyes. In 1,000,000,000, the sun will have swollen into a red giant and swallowed the inner planets. In tens of billions, distant galaxies will slip beyond our reach as space keeps expanding. The universe of the far future will be lonelier, colder, more spread out. Yet the memory of that first smoothness will still be written into the microwave background, growing fainter, but not vanishing. Future instruments may sharpen our view of that memory. Space-based observatories, designed to measure the faint twist of light called polarization, could reveal ripples left by primordial gravitational waves, the tremors of the earliest moments. If those tremors are found, they would strengthen the case for inflation. If they are absent, or if their pattern looks wrong, the whole story may need rewriting. Some researchers wonder whether the smoothness has nothing to do with inflation at all. In cyclic models, the calm comes from a long, slow contraction before the bang, a phase that quieted every wrinkle before the bounce set expansion in motion. In that picture, our smooth beginning is the polished end of an older cosmos. Inflation would then be unnecessary, or at most, a small extra step, layered on top of something more ancient. Others suspect the smoothness is a selection effect. In eternal inflation, most regions never settle down. Only the rare pockets that happen to be calm enough give rise to stable universes, where observers can eventually appear. From inside such a pocket, the sky looks smooth, because no other kind of sky could have grown a watcher to see it. The calm is not chosen, it is required by our own presence. There is also the entropy puzzle, raised by careful thinkers who count the ways a universe can be arranged. A smooth, low entropy start is astonishingly rare among all possible starts. Inflation by itself does not explain why nature picked such a rare arrangement. Something older, or something outside the usual rules, must have set the dial. The future of this question depends on data that does not yet exist. Better maps of the oldest light, sharper measurements of the largest scales in the sky, where any pre-inflationary fingerprint would be strongest. New detectors that can listen for the faint hum of gravitational waves stretched across cosmic time. Each of these tools is being built, planned, or dreamed about now. Each may take decades to bear fruit. In the meantime, the universe keeps changing. Stars are being born in quiet nurseries of gas and dust, their glow softening the dark. Old stars are dying, seeding space with the heavy elements that will build new worlds. Galaxies drift and merge in slow gravitational dances, and through it all, the smoothness of the beginning remains, a faint, even warmth in every direction, a whisper from a moment we cannot yet explain. Perhaps a future generation will look at their sharper maps and see the answer written plainly. Perhaps the smoothness will turn out to have a simple cause we have not yet imagined, or perhaps the question will deepen further, revealing more layers of mystery beneath what already puzzles us. The universe of 1 billion years from now will be a different place. The calm at its beginning will still be waiting, patient, unresolved, quietly asking why it was ever there at all. There comes a point in every deep question when the question turns around and looks back at us. We ask what came before inflation, and the asking itself becomes strange. We are small, warm creatures on a small, warm planet, made of atoms forged inside stars that lived and died long before our sun was born. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was cooked in the hearts of ancient suns, then scattered across the galaxy when those suns collapsed. In some quiet way, we are the universe asking about itself, and yet the universe may not be able to answer. Some questions in physics are hard because we lack the tools. We can imagine building a better telescope, a colder detector, a longer baseline. Given enough time and patience, we might learn what dark matter is, or where the first stars ignited, or how life began on our world. Those are hard questions, but they feel reachable. The question of what came before inflation is a different kind of question. It may sit past the edge of what any measurement can ever touch. Inflation, if it happened, erased its own beginnings. It stretched a tiny patch of space by a factor so enormous that whatever came before was smoothed into invisibility. The wrinkles were flattened, the details were washed out. The universe we can see was cleaned by that expansion, and the dirt of its origin was carried away into regions we can never observe. This is a strange kind of limit. It is not a limit of technology. It is a limit written into the structure of the cosmos itself. Light from before inflation cannot reach us, because there was no light yet, and because the geometry of space during inflation prevented signals from propagating in the ways we understand. Whatever was there is not hidden behind a wall we might one day climb. It is hidden behind the very idea of climbing. Some thinkers find this humbling, others find it freeing. If certain questions lie forever beyond the reach of experiment, then physics, for all its power, has a horizon of its own. Beyond that horizon, we are left with mathematics, philosophy, and the quiet exercise of imagination, the no-boundary proposal, the tunneling from nothing, the eternal inflation of endless bubble universes. These are ideas that may never be proven or disproven. They may remain, always, in the space between what we can calculate and what we can confirm. And still, the calculations matter. Even a theory we cannot test can sharpen our thinking. It can show us which questions are well formed and which dissolve on closer inspection. The word before, applied to the origin of time, might be one of those dissolving words. It might mean nothing at all, or it might mean something we have not yet learned to say. The mystery is not only what happened. The mystery is whether the question is even the right shape. Consider the strangeness of your own position tonight. You are lying still, breathing slowly, resting inside a body built from the ashes of dead stars. Those atoms have been in existence for billions of years. They passed through gas clouds, through planets, through oceans, through countless other living things, before arriving in you, and every one of them traces its history back through the long cooling of the universe, back through the formation of the first light elements, back to the fireball that followed inflation. Beyond that, their history disappears into the same fog we have been sitting with all evening. There is a kind of intimacy in this. The mystery of what came before is not distant. It is written into your fingertips and behind your eyes. You are not separate from the question. You are the question, wrapped in skin, wandering about itself under a dark ceiling. Perhaps that is why this mystery does not feel frightening. It feels quiet. It feels like coming home to something older than home. The universe has been unfolding for nearly 14 billion years, and for a brief while, in this small corner, it has become aware enough to look back at its own beginning. Whether it will ever fully understand what it sees, we do not know. Whether such understanding is even possible, we do not know. What we know is that the wandering itself is real. The questions are real. The stars overhead are real, and the atoms in your body, once forged in furnaces older than the earth, are settling now into the soft geometry of sleep. The universe is resting inside you. The mystery is resting with it. And there is no need, tonight, to solve anything at all. And so, we come to the end of our long walk through the dark. We have stood at the edge of the first fraction of a second and looked back and back and back again, into a place where the words we use begin to lose their meaning. We have listened to theories about false vacuums and quantum bounces, about bubble universes and gentle boundaries where time simply stops existing. Each idea was beautiful. None of them was final. That is the shape of this question, and it may always be the shape. What came before cosmic inflation is not a puzzle with a hidden answer waiting to be found in the back of a book. It may be a doorway that only opens partway, no matter how carefully we press against it. Our best minds have built their most careful mathematics, and still the door hangs there, half open, showing us only shadows on the other side. There is something quiet and lovely in that. Not every question needs to be closed. Some questions are meant to be lived with, the way one lives with a slow river or a familiar mountain. They shape us simply by being there. Picture, for a moment, a small blue-green world turning slowly in the dark. Its oceans catch the light of a nearby star and scatter it in long ribbons of silver. Clouds drift across the continents in slow spirals. On the night side, faint pinpricks glow where living things have gathered together. The world turns and turns and does not hurry. Above that world, farther out, a moon hangs in the black. It is pale and pocked and patient. It has watched the tides for billions of years and asked nothing in return. Around them both, the great wheel of a galaxy slowly rotates, its arms trailing dust and young blue stars, its center glowing warm and gold. That galaxy is one of countless galaxies, each one a soft island in a sea so wide our minds cannot really hold it. And every one of those galaxies, every star, every quiet ocean and drifting cloud, came from the same moment we have been circling all night. Whatever happened before inflation, whatever seed or bounce or boundary set everything in motion, it led here. It led to warm rooms and soft blankets. It led to the sound of your own breathing. It led to the strange, wonderful fact that a small collection of atoms can lie in the dark and wonder about its own beginning. There is a kind of comfort in being this small. The universe is not asking you to solve it tonight. The mystery does not need your answer to remain beautiful. The scientists working on these questions will keep working, patiently, generation after generation, adding one small stone at a time to a wall that may never be finished. That is enough. That has always been enough. Maybe one day a satellite will spot a faint pattern in the oldest light and give us our first real clue. Maybe a new mathematics will show us that the question itself was shaped wrongly, and a better question will take its place. Maybe the answer will come in a lifetime, or in 1,000 lifetimes, or never. All three of those possibilities are honest. All three of them are all right for now. Let the question rest where it has always rested, in the soft dark before the first light. Let inflation remain the flash we can almost see. Let whatever came before it remain the deeper quiet we can almost feel. Some things are not less real for being unknown. They are simply waiting, without hurry, without need. Outside your window, the same sky hangs that has hung above every human who ever wondered about beginnings. The same distant galaxies, the same patient stars. You are held inside all of it. Small, yes. Brief, yes. And also part of something so old and so wide that our best theories still stand at its edge, hats in hand, listening. Let your shoulders soften. Let your breathing slow. Let the questions drift like clouds across a night sky, present, but no longer needing to be answered. The universe has been keeping its secret for nearly 14 billion years. It will keep it a little longer while you sleep. Somewhere, a slow river of stars is turning in the dark. Somewhere, a quiet ocean is resting under moonlight. Somewhere, the first moment of everything is still whispering to itself in a language we are only beginning to learn. And here, in this small, warm place, you are allowed to simply rest inside the wonder of it. Subscribe for a brand new space topic every night. On tap, and something incredible is waiting for you tomorrow. Sweet dreams.